paper, Black Holes, Warp Drives, and Energy Conditions. Now, if you've been paying attention for a long time, watching my content, this paper might seem familiar because this paper seems to be commenting on a result that I made a video about a few months back. But I haven't read this paper, so we'll see what it's about. So let's just go through the abstract really quick. Oh, by the way, this came out 5 days ago. It's on the preprint server, not yet been published. This is a preprint, and this is, in some sense, it's a peer review. I mean, you know, I'm not actually going to work out their math, but you know, it's in some sense a neat thing to do for the public. And it is by names that I cannot pronounce, but it's interesting nonetheless. Right. So following the work of H. Ellis, we study warp drives in the gravitational field of a Schwarzschild black hole. Remember, that's the non-rotating, simplest black hole that you can get. We find that as long as the warp drive crosses the black hole horizon at subluminal speed, the horizon would be effectively absent inside the warp bubble, meaning that you can escape the black hole. Moreover, we discovered that the black hole's gravitational field can alleviate the violations of the weak energy condition, WEC, and the null energy condition, and therefore decrease the amount of negative energy required to sustain a warp drive, which may be instrumental for creating microscopic warp drives in lab experiments. We also consider the thermodynamics of a warp bubble interacting with a black hole and point out some paradoxes that may indicate a gap in our understanding of them from the thermodynamic point of view. So, again, if you had seen my videos in the past, you would know that there was a paper that came out, I don't know, 3-4 months ago, that made the claim that, in fact, you could escape a black hole with a warp drive so long as you're traveling slower than light, which is really interesting, that you actually have to travel slower than light to escape the black hole. And it seems like they're going to come to the same conclusion. But let's read it. It's only a 6-page paper, so it'll probably be done in about an hour and a half. Anyway, let's start with the beginning. So, the concept of warp drives was first introduced by Miguel Alcubierre in his seminal 1994 paper and elaborated on by Jose Notario in 2, as well as in a multitude of other works. So I've actually read both of these papers, the Alcubierre paper and the Notario paper. They're both quite interesting, both quite readable. This is the standard: you contract space in front of you and expand space behind you. By the way, if you're just joining us, the title of the paper is above my head. A warp drive is a solution of general relativity that has the appearance of a bubble propagating on some flat or non-flat spacetime background. The observers inside the bubble are in an inertial reference frame. An inertial reference frame, by the way, is just a reference frame where you don't feel like you're accelerating, where you don't feel like you're moving at all. It just feels like you're floating. Which means warp drives do not require external energy sources to accelerate, and they may move at any speed. Great. In principle, including superluminal. So the idea behind a warp bubble is that the space moves, you don't move. So it doesn't require a whole lot of extra effort. You can just hop in your warp bubble and travel to Andromeda in a day. This makes them a viable candidate for interstellar travel, but they have one significant downside. In order to sustain a bubble, one requires exotic matter with negative energy density. Now, this is not antimatter here. I have to be super clear there. This isn't antimatter. This is matter that has negative mass. As far as we know, no such thing exists, which is why warp drives are essentially in the realm of science fiction, right? As described by H. Ellis, the Schwarzschild metric, which describes a black hole, can be mapped to a warp drive type metric with the use of a coordinate system known as the Painlev-Goldstrand coordinates. I'm probably mispronouncing that. Painlev, which makes it possible to embed a warp drive in a black hole background. A different but somewhat similar proposal to directly combine a warp drive and a Schwarzschild black hole is put forward in 24. Let's actually go down and look at the references just to see what was, to see if we can find the paper that I was reading a while ago. So these are quite old papers. Let's see, do they actually cite the paper that I was looking at recently? This is from 99. That's quite old. 2009, 2012, 2017, 2019. I think it was this paper, actually. I think it was this paper by Schuster, Santiago, and Visser. Let's just open that up just to take a look really quick. No, it wasn't that one. Was it this one, maybe? From 2021. Nope, not that one. Maybe they don't cite that paper that came out quite recently. Okay, that's fine. Anyway, let's go back to reading. Right. In section 2 of this paper, we briefly discussed the basics of Alcubierre warp drives. Then in section... Oh, so they're going to do a review, which is handy. Then in section 3, we consider the situation when the warp drive is embedded in the exterior of a black hole, in the limit when the warp bubble is much smaller than the black hole and moving in the radial direction towards it, and demonstrate that the black hole's gravitational field affects the warp drive energy conditions, making it possible to alleviate the violations of the weak energy condition and the null energy condition. So, by the way, just so we're clear, the whole business with requiring negative energy density, that's what they're talking about when they say weak energy condition or null energy condition. These are technical descriptions of the idea that you need some sort of negative mass. And it looks like that they're actually going to embed the warp drive in a black hole going towards the center. I don't understand why. Maybe because it's easier to make a warp drive if it's going towards the center of the black hole. This implies that an external gravitational field can decrease the amount of negative energy required to sustain a warp drive, a fact which may be useful for the development of microscopic warp drive-like structures in a lab. Cool. We also show that as long as a warp drive that crosses the black hole horizon is subluminal, the horizon is effectively absent inside the... I actually may have already read this, but we'll do it anyway. Inside the warp bubble, i.e. both an incoming and an outgoing geodesic can pass through the patch of the horizon that is inside the bubble. We generalize these results to the case of arbitrary warp bubble size and direction in section 4. Then in section 5, we consider the thermodynamics of the warp bubble crossing a black hole horizon. We conclude in section 6. Okay, fine. Just a summary of what they're about to do. Fine. So let's start with a brief overview of warp drive physics. This is quite a sci-fi section title, isn't it? I was watching Star Trek Prodigy the other day with my wife, and there were all of these jokes about, didn't you read the Temporal Mechanics 101 textbook? And that's what this reminds me of. Right, so a warp drive metric, remember, a metric, if you're new to these peer review lives, you'll learn, but a metric, remember, is just a way of describing how you measure distances and times, and in particular, in spacetime, and in particular, it's what basically captures all of the curvature of spacetime. A warp drive metric, as defined by Notario, is given by this formula. So, I have to explain what these symbols are, even though longtime viewers have seen these before now. So again, the metric is roughly a squared plus b squared equals c squared, right? So the metric is telling you how to measure distances and how to measure times. The only difference is that because we have time and space, the time comes with a minus sign and the space comes with a plus sign. So rather than a squared plus b squared plus c squared equals d squared, say in 3 dimensions for the Pythagorean theorem, you would have negative a squared plus b squared plus c squared equals c squared, or equals d squared, or whatever. So here we have minus dt squared. This is just a small increment in time. This is all, it's all written in terms of like small increments because, you know, it could change place to place. And then we have a spatial component. So here we have that there is a term that just tells you that if you increase your position, if you move a little bit in the, say, x direction, this I, by the way, is just counting from 1 to 3. That's what this big summation means. So if you move a little bit in the x or the y or the z direction, that contributes to the distance that you're traveling, of course. But there's a modification. This modification basically tells you how fast your warp drive metric is moving, because it tells you, it gives a relationship between x and t. And so sitting still will correspond to some sort of motion in this warp drive metric. They're going to explain more and more details, but that's the rough gist. There's a question, why is it always plus, 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 minus? It's just convention. In fact, they even say it here. This is the mostly plus spacetime signature. You could use minus, 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 plus, or mostly minus, but relativists tend to like mostly plus, and particle physicists tend to like mostly minus. It's just a preference thing. It doesn't actually matter. By the way, if you're new here, supporting the live is a cool thing to do. If you can, like the live, share the live, subscribe if you're interested. But anyway, let's keep going. So in ADM variables, are just, it's a standard set of coordinates that basically split up space-time into space plus time. So you have dt, or you have t as your time, and then you have x as your space. So in ADM variables, one can define it by setting the lapse function n to 1. The lapse function basically tells you how time warps as you move up and down, or as you move through space-time. And they're just saying, look, just fix the time coordinate so that you're moving at a constant rate through time. And the inner metric to the delta function. So that's that. Basically, they're just fixing coordinates so that everything looks nice. Right. So the warp drive itself is a deformation of the metric localized in a bubble. In a bubble-shaped region that is moving on some flat or non-flat space-time background. Oh, we got a goose hat? Thank you, Ethan. I can't see. I can only see the... Anyway, but thank you. The goose hats are the best. Its velocity. So the velocity here is given by... So again, that superscript I, that's just telling you the... like the x speed, the y speed, the z speed, basically the speed in the various directions. And this is just telling you it is the derivative of the spatial position with respect to time. But here, that subscript s is telling us it's the position of the bubble's center. Fine. Okay, so this is the speed of the warp drive. Assuming that the bubble is moving along the x-axis on a flat space-time background, the metric would be given by this formula. So this is just a simplification of this formula here. All they've done is they've simplified it so that the ni terms are only in the x direction. So ny and nz are both 0. And then also they have that they've written out a new formula for ni. They've simplified it so that you have a speed, and then it's something like a fall off term, so that like if you move, it's basically telling you where the bubble is. So you have the minus dt squared, that didn't change. And then you have dy squared and dz squared. That's just the terms from this component. And then you just have your, this is your warp bubble factor. So here, this is just telling you that your warp bubble only moves in the x direction. So this is known as the Alcubierre metric. This just is the Alcubierre metric. Here, f is just f is a function of distance from the center of your warp drive, and it just describes the shape. So here, it's just telling you that this is that r sub s, which is what this function f is. It's just the distance from the center of the warp drive. So that's all this is capturing here. So it's basically saying that if you're sufficiently far from the center of the warp drive, then your spacetime is flat because this f will be 0. And if you're close, or it'll be flat and uninteresting. If you're at the center of the warp drive, this f will be 1, and then your speed will just be v. And that can be greater than the speed of light. In fact, they say here, at small values of r sub s, meaning when you're close to the center of the warp drive, f of r sub s equals 1, meaning that essentially your spacetime metric is just dx, this particular part is just dx minus v sub s dt. So this is just telling you you're moving through space at v sub s. And then they go on to say, after r sub s approaches some value capital R, the size of the warp bubble, f of r sub s steeply decreases to 0. So it's basically saying inside the warp bubble, you're moving through space-time at a particular rate. Outside the warp bubble, you're not moving at all. As was shown in 1 and 21, these are just some references. The first one is the Alcubierre warp drive. The Alcubierre warp drive violates both the weak energy condition and the null energy condition. This is the whole, it requires negative matter, or negative mass matter. Namely, the former says that the inequality, we can talk about this, what this means, but this is T mu nu contracted into n mu is greater than or equal to 0. So let's read the rest of the sentence and then I'll break down what they're saying. So T mu nu is the stress energy tensor, should hold for any time-like vector n nu. So what this equation is basically saying, so T mu nu basically tells you how much energy and momentum and stress there is and momentum flow. T mu nu tells you how much stuff there is, whether the stuff has positive energy, negative energy, whatever. And so in particular, when you multiply this T mu nu by two time-like vectors n, that's what these are. By the way, let me back up. A time-like vector is just, it's a path, it's basically an arrow that points in space-time in the direction of increasing time, not in the direction of increasing space. So if you think of time as flowing upwards and space as going to the sides in all directions, then a time-like vector points up. And so in particular, what this means is that this is a measure, this quantity here, T mu nu and n mu n nu, is roughly a measure of how much energy somebody sees around them if they're just floating through space. So you could, in some sense, this is basically saying that for any observer moving through time, they should see a positive amount of energy. That's what this inequality is saying. So that is the weak energy condition, namely that that there should always be positive energy around you. That's it. If in particular, this is exactly what they're saying. If we choose as a time-like vector -1 in the, so again, this is just an observer that's traveling forward through time and not moving at all through space. And we can tell that, by the way, because if we go look at n mu, this is the time coordinate. So remember that the order of coordinates is we have t is the first one, then we have x, y, and z. So here, they're saying that this is a vector which is pointing in the time direction, and then not pointing at all in the space direction. And so this is a vector, this is just somebody not moving through space, just moving through time. And then you can actually compute, using this time-like vector, you can actually just compute what t mu nu is. Or you can compute what this quantity on the left-hand side is by plugging it in. Well, using this metric, you can plug it into the Einstein field equations, which we're not going to get into. And then you can use those to evaluate the stress-energy tensor. And then you can just compute what the energy density is of the warp field. This basically tells you how much energy the warp field has for an observer. So energy is observer dependent, so they've just chosen an arbitrary observer, a specific nice one. But you can show that this particular observer will find that the energy density is this much. Now, here I should explain what this is. This k here basically tells you how curved the space is. And this k squared is just, it is the, yeah, so I'm not going to go into the details of this, but this term here basically it's basically roughly a measure of how curved your space is embedded in space-time. So like you can imagine like you have like some wild curved space, and each slice of space is very, very curvy. It's called the extrinsic curvature, or at least it's closely related to it. So the extrinsic curvature here is k. As the extrinsic curvature tensor is flat, as the extrinsic curvature tensor for flat intrinsic metric hij is just given by this. This is just a formula for k. It's a formula for k, which is the extrinsic curvature. It tells you how curvy the space is. It's just written in terms of these set of functions here. So we can go back and we can look at the formula for it. It's just the partial derivatives of those functions in a symmetric way. So you take the partial derivative with respect to x of ny plus the partial derivative with respect to y of nx, for example, and that would give you kxy. Just replace ij, replace these with x, y, z, whatever you want. So the upshot, because we know that the energy density is given by this formula, we know that the extrinsic curvature is given by this formula, and we know what n is because n shows up in our metric here. It's basically just this in the x direction and it's 0 in the other direction. Then you can just explicitly compute what the energy density is, and you find out that it's actually just negative. You get a negative sign. So everything here is positive, and you have an overall negative sign, which means that the weak energy condition is negative. So if you are trying to measure the energy in your warp drive, you get a negative number. So this is a problem. In particular, they say, so the weak energy condition is explicitly violated. And then they're going to do the same thing with the null energy condition. The null energy condition is roughly the same, except instead of having time-like vectors here, these are vectors that it is roughly the average divergence, by the way. Instead of plugging in time-like vectors, so this is as measured by somebody who's moving through time, rather, yes, by the way, this is being recorded. The null energy condition just says, well, if these vectors are light-like, meaning that if you were to travel along a beam of light, how much energy would you measure? And so the null energy condition can be done the same way, except your null vector, you have to have equal speed in both the time and space directions. Remember that in relativity, a beam of light travels through space at the same rate that it travels through time. So that's why we have 1 and 1, because that's what it means for something to be a beam of light, to be a null vector. We say that beams of light take null trajectories because their space-time interval, which is evaluating their metric, it gives you 0. So if you have -1, if you have -1 squared plus 1 squared, you get 0. So hence it's called null. Anyway, So you can compute, again, plugging this in, much the same that we did for the weak energy condition. You can just plug it in, and you can compute, and then you end up with a formula for the for T mu nu, N mu, N nu. And, you know, there's just some arithmetic happening. Not arithmetic, I shouldn't be so blasé. There's some calculus that happens. But at the end of the day, what you find is that the null energy condition is also violated because it's proportional to the weak energy condition violation, so long as you take appropriate averaging. They actually give a point here. It's interesting to note that the ratio between rho and txx is exactly 3, which is interestingly related to the Casimir effect, which is cool, I guess. So suffice it to say, regardless of how you measure it, you find that you are violating, you know, positive energy conditions, meaning that you find that no matter how you slice it, you have, you need something that has negative energy, like negative mass, for example, would do it. So we can't build warp drives, or can we? Right. So that's their review for the Alcubierre drive and the Notario drive. Now, let's get a little bit more sophisticated. Now let us consider the more generic situation where the bubble propagates on some stationary, non-flat background. So remember, here they have a flat background. So the way that we can check that it's flat is just imagine that you're far away from the warp drive. If you're far away from the warp drive, this f is just 0. And then you have minus dt squared plus dx squared plus dy squared plus dz squared. And that's just a flat metric. That's just normal Minkowski spacetime, which is the realm of special relativity. There's no gravity there. But now they're going to try, instead of putting the warp drive in a flat background, so just like normal flat space, they're going to try to put it in some non-flat background. And that means that they actually have to alter the metric a little bit. So the components of the shift vector, this basically tells you how fast a point is moving from a time slice to time slice. The shift vector has a different form. So what's the, let me back up and explain. So for a generic metric, so long as the lapse function is 1, you can always write a generic metric in this way. Namely, you have two time slices. So you have two slices of space, one after another. Basically, this ni tells you how much or how far one point moves on the next time slice. So if you move forward in time a little bit, that point gets sent somewhere else, perhaps not directly above. If this ni was 0, then a point on the first time slice would be sent to the same point on the time slice above. But if ni isn't 0, then it's sent somewhere else. And so that's how you get a warp drive from this, because you just send a point here to a point really far away. So they have to adjust the shift vector, because now even without a warp drive, there's already a shift vector built in, because you know the shift vector just describes how time slices relate to the next time slice. And so here they have this extra term here. This is the shift vector associated with just the background geometry. It has nothing to do with the warp drive. Ignore this. Or if set f to 0, which would make it so your warp drive is turned off, then you would just have a shift vector that just corresponds to whatever background metric you're putting it on. So if you want to incorporate a warp drive, you then have to turn on these f of r. So in the particular case, when the background metric is spherically symmetric, so think like a round black hole, ni sub b, so again, ni just tells you how much a point shifts when you move up in time, and b is just background. This is given by a particular formula. So the ni is just going to tell you how much you shift as you move around, and in particular, because it's spherically symmetric, you can write it in this particular form. This is basically just saying that the lapse function, this n, only depends on your distance from the center of your spherically symmetric spacetime. And then the amount that you move just depends on your kind of the angle that you're making with respect to some fixed vector. So in this case, the background metric can also be written in a more compact form in spherical coordinates. So basically, and it's just a choice. You don't have to do this. But rather than using x, y, and z, you can use the distance from the center, and then you can use like theta and phi, your two angles. Just a different choice of coordinates, but it'd be like specifying latitude, longitude, and then how high you are above the Earth, rather than saying like, I am at this place and that place. I'm like 5 meters to the left, 2 meters forward, and then 8 meters up. It's just a different choice of coordinates. But spherical coordinates are nice when your space-time is spherically symmetric. So you can write it like this. This is the background metric. And then beta just shows up here as a kind of a lapse in your radial coordinate. So it just tells you how much do you shift. So imagine you have a spatial slice that's spherically symmetric. If you move forward in time, you'll either move in or out by some amount. And that's all they're saying. This beta controls how much you move in or out when you shift forward in time. And so as shown by Painlevé and Goldstrand, the Schwarzschild metric has this property. Okay, this is the Schwarzschild metric. This is the metric for a black hole, for your most boring black hole. So you can see in particular that you get like things that go to infinity. Like if this denominator becomes 0, then you have things that blow up. So this is where you get like event horizons. In particular, when little baby r, that's your distance from the center, when that's equal to your Schwarzschild radius, which is 2gm, that means that you are at the point of no return. That's the event horizon. It's where the metric starts to behave badly. So this is the Schwarzschild metric. So you can actually write this metric in this form if you choose beta is the square root of the Schwarzschild radius divided by the distance from the center. And this is just by doing a coordinate transformation, which is always a mess to do. Doing coordinate transformations can be annoying, but don't worry about how they got this. This is something that you can actually derive. You can like prove this mathematically, but the point is if you replace all instances of t with capital T minus this integral, then you can write your Schwarzschild metric in this form. And so then the idea is that, I guess some fellow named Ellis, who is quite famous, is that the Ellis? Anyway, as suggested by Ellis in 23, this is a reference, this relation can be used to embed an actual warp drive within the exterior of a black hole by replacing the shift factor by a different, the shift vector by a different shift vector. That's the point. So they're basically going to be using this shift vector rather than this shift vector, where this is what goes in here. Where were we? Yeah, so they're just writing down what the shift vector actually will be in this form. Well, it's roughly in this form. It's not quite. So they're going to be doing it in. Are they not going to be using spherical coordinates anymore? That's a bummer. But okay. So they're actually using Cartesian coordinates, x, y, and z. So here we have that the warp drive is moving in the x direction. Yeah, they're assuming that the warp drive is moving along the x-axis. So the shift vector is 1 minus f. Remember, f just tells you, it's just a function that tells it's 1. F is a function that's 1 when you're at the center of the warp drive, and then it's 0 when you're outside the warp drive. That's the way to think about it. And so you can just evaluate this thing, you just evaluate this thing when I is 1. Sorry, when I is x, rather. And you just end up with this. I mean, like, if you just look at this, they just left out this of r sub s here. So it's just 1 minus s times the square root, and then you just have x over r, since they're looking in the x direction, minus f times v. They're just dropping some subscripts and stuff like that. But that's just all, it's basically the same thing. And then they consider in the limit in which the characteristic size of the warp drive, which is described by the support of the function f. The support of the function just tells you where is the function f1 and where is the function 0. So they want to look at a very, very small warp drive. So it's much smaller than the Schwarzschild radius of the black hole. In this limit, the lapse functions are close to 0. By the way, the reason they know that is because the lapse functions in the y and z direction. Why is that close to 0? Let me think about this. So if this is our lapse function, and the warp drive is moving in the x direction, then okay, so I see. So v sub I should only be in the x direction. And so this term turns off when you're in the y or in the z direction. And so all you're left with is this. But f is close to 0 in almost all cases. Sorry, does this actually make sense? Yeah, F is close to 0. But how does this get us to... So they want the support of F to be much smaller than the Schwarzschild radius. So the Schwarzschild radius should be quite large. This function is close to 0. So this is roughly 1. Why would that make the lapse function close to 0? I guess if you're near... Okay, so I can see why that would be the case, so long as you're near the event horizon. If you're near the event horizon, then you're... Yeah, okay. So that's not written particularly well. But the point, they're assuming that you're near the event horizon, not like near the core where things get really bad, because otherwise your R gets really, really small. If you're near the event horizon, so capital R is about R sub G, then Y, in order for this to not be 0, you would need that Y to be quite large. But if that's the case, yeah, so this checks out. But they didn't write it very well. Anyway, so in this limit, we have that the lapse functions are basically 0, and the energy density, 7, reduces to this function here. So they just computed the energy density over here. They just did the computation given the metric that they've established. And they find that it is in some sense, it's smaller. So they're neglecting terms that are y over r and z over r. So again, they are near the event horizon, near the warp drive. So y over r and z over r are quite small. From this, once again, neglecting those terms, which is what they did to get that this is roughly 0, we obtain a formula for rho. And so let's stare at this for a minute. So the old one, the regular one, that was here. So we have f squared v squared over 32 pi g with a minus sign. So we again have f squared, and then we have a term that looks like v squared over 32 pi g. So it's still negative. But in particular, they're increasing this term here. And then they're also adding, okay, I see. So this is interesting. Thank you for the garland, Robald. I appreciate that. So if y and z are small, so this is f prime squared of y squared plus z squared over r sub s squared. They're actually going to tell us what's going on, so why don't we just keep reading? Hence, for negative v, i.e. the warp drive moving towards the black hole, so here, if v is negative, so this is just the absolute value speed of v, is greater than some proportion of square root of the Schwarzschild radius divided by the distance from the center of the black hole, they say that the amount of negative energy required to sustain a warp drive would be decreased by the black hole's gravitational field. So what they're saying is that if you make v sufficiently small, then this term can become smaller. Make v negative, make it smaller. And you end up with requiring less energy, less negative energy, to make your warp drive. Otherwise, or if the warp drive is moving in the opposite direction, it would be increased. So if you want to escape a black hole, you actually need more negative energy. So, by the way, just so you know, g, this capital G here, that's Newton's gravitational constant. It's some small number. It's like 6 times 10 to the minus 11 in SI units or something like that. So, this means that the external gravitational field can alleviate the violation of the weak energy condition in warp drive metrics. So this kind of makes sense, right? What they're trying to say is that if you have a warp drive inside a black hole, or I should say, if you have a warp drive near a black hole and you're headed towards the center rather than away from the center, it's actually easier to make a warp drive metric. And that kind of makes sense because the black hole's kind of tugging you along already. All right, well, then they're also going to look at the null energy condition. You can write out the other components of the stress energy tensor. We're not going to go through the calculations. It's a mess to do. and then you can do some more computations. Don't worry about them. They're going to end up with a formula in the same way that they did before, where the first term is just the total divergence, second term, blah, 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 blah. We can skip this. This is just more and more calculation. This means that for a vector oriented along the x-axis, the averaged expression would once again yield 4 times the energy density, as in 14, so the violation of the null energy condition would also be alleviated by the black hole's gravitational field. So, this is good. Means if you're headed towards the black hole, it's easier. So, as shown in 28, it may be possible to create warp drive-like structures within Casimir cavities in a lab. So it appears a promising direction to investigate how they would be affected by an external gravitational field, and whether such a field can serve a practical purpose by making it possible to realize a warp drive with a lesser amount of negative energy, or vice versa, to amplify the effect of the warp drive. So they're just saying that actually this work actually does have some potentially practical applications, especially if we want to make one in a lab. They're going to make another note. Let us note that the 0,0 component of the metric tensor is approximately this. So the 0,0 component is basically tells you how fast time moves, and this is really important. And this is the key observation. So remember, if we go back and we look at the Schwarzschild metric, when the time component becomes 0, that's where the event horizon is. So when your distance away from the center is the Schwarzschild radius, that tells you how far away the event horizon is. So in particular, when 1 minus RG divided by RG, that's equal to 0. When this whole thing in parentheses is 0, you're at the event horizon. So all you have to do is look at when the dt squared term becomes 0. So that's what they're doing. So they've now adjusted the metric by adding the warp drive in. So their metric has changed because they have this formula for nx, and then they plug it in here. So now you can evaluate the 0,0 component, which is the time piece, and you get this formula. Thank you. Thank you for telling me to drink more water. By the way, y'all, like the live. It's a cool thing to do. Right. So what they're saying, so they say that the 0,0 component of the metric is approximately this. And so the horizon would be effectively absent inside the warp bubble so long as it's subluminal. So if you take f being less than 1, then that means that there's nothing that you can do. Or sorry, if you take v as less than 1 and f as 1. So if you take f as 1, sorry. If you take f as 1, so you're at the smack dab at the center of the warp bubble, then this term goes away. And then the only thing contributing to the time component of the metric is just it's -1 plus this thing squared. So long as so again f is 1, so it's just -1 plus v squared basically. So that means that as long as v is less than the speed of light, here the speed of light is 1, that means that the event horizon just goes away. There is no event horizon if you're inside the warp bubble moving outwards slower than the speed of light. There's just no event horizon, which means that you can escape. So funnily enough, you can escape a black hole with a warp drive, but only if you move slower than light, which is super cool. It's such a cool result. I've seen this before, but it's really, really cool. So they're going to give a little bit more details. One can understand this more precisely by considering a light ray moving along the x-axis with the geodesic given by this. So here they're describing the motion of a light ray, a beam of light. And the motion is described by, remember what I said? In order for it to be a light ray, if you evaluate the metric along the path that the light ray takes, it should be 0. So you have a minus piece that comes from the time component, and then you have a plus piece that comes from the space component. Here, the space component is dx plus the shift function, or the shift vector, dt squared. So you have to just add that term. This thing is supposed to be 0 in order for it to be a light ray moving in a direction, in this case in the x direction. Oh, we have a picture. Here we once again neglect the term ny squared plus nz squared dt squared, which is reasonable because those are small. Dividing this expression by dt, which you're allowed to do. This is a physics paper. You're allowed to divide the expression by dt squared. So they're just going to take this and divide the whole thing through by dt squared. Calculus teachers turn away. Then you end up with this equation. So you have dx squared over dt squared. You have a 1 coming from dt squared over dt squared. And then you have some cross terms, dx over dt times nx, and this cross term here. And so what they find in particular is this tells you the rate at which it moves in the x coordinate relative to the t coordinate. And so you can actually just solve for dx dt, which is the speed of light, or it's the speed at which it's moving in the x direction relative to the t coordinate. And so this gives you that this is coordinate speed. It's not actually the speed of light. Speed of light's always the speed of light. This is coordinate speed, so this is relative to the coordinates that we put down. Yeah, this is just the quadratic equation here. And so then you can solve for when this equation is equal to 0. You get that dx dt, coordinate speed, is equal to minus the shift function, plus or minus 1. The plus and minus sign corresponds to the outgoing and incoming geodesic respectively. So in particular, if a light ray is falling in through the warp bubble, then that means that its coordinate speed will be faster than 1, so it's going to fall in faster. On the other hand, if it's going out, then its coordinate speed will be slower, because you have 1 minus nx. And the Schwarzschild radius, i.e., so we want to evaluate this at the Schwarzschild radius where the event horizon would be. This is r sub g. The roots are given by this. So they're just plugging in what they know nx to be. Nx is known to be this thing here, and we're assuming that you're at the center of your warp drive, so f is equal to 1. Well, I guess they're not assuming that yet, but yeah, you can plug in nx here, and then you can plug that in here, and then you can just plug in r equals rg. And then you get a coordinate speed. So this is f times v plus 1. That's the speed at which you're moving. And so these are the two roots. And then you also have f times v plus 1 minus 2. So the important point here, so this is you have a light beam that's potentially going out, which is described by this formula. The outgoing geodesic doesn't have 0 speed, so long as v is greater than minus 1, while the incoming one does not vanish so long as v is less than minus 1. So that means that for v is for the actual rate of speed, v, so long as your speed is less than the speed of light, remember the speed of light is 1 in these coordinates, we would have an outgoing and an incoming geodesic passing through the intersection area between the warp bubble and the black hole horizon. Let's look at the picture. So is this drawn in paint? Pretty sure this was drawn in paint. So here we have a warp bubble, the blue dashed line, crossing the black hole horizon, which is the black line. Outside the bubble, there are only incoming null geodesics. So you can think of the green arrows as light rays going out, the red arrows as light rays going into the black hole. And so what you find is that so long as the warp bubble has a speed that's slower than the speed of light, there are both ingoing rays and outgoing rays. There are light rays that can escape. This makes it possible for an observer inside the bubble from the center to send a light signal to the outside from behind the horizon. So if you're sitting here behind the horizon, then you can actually send a signal to someone outside the horizon so long as you have a warp bubble. This means that an observer inside the warp bubble that has crossed the horizon can nonetheless send a light signal out of the black hole. So this is one of the very strange things with warp drives. You don't even have to go faster than the speed of light in order to escape a black hole or communicate from the inside of a black hole to the outside of a black hole with a warp drive. Probably why warp drives are impossible, but let's keep reading. We may also consider the generic case, where the warp drive is not necessarily much smaller than the black hole, and not necessarily moving in the radial direction, i.e. n, y, z are non-negligible. Okay. Once again, following 25, one can write the energy density in this form. Okay, here's just a formula for a generic version. And so then if you take your lapse function to have this form that we've already done before, the first term vanishes, that's this term here. And the second term becomes this horrible formula. Oh, that's awful. It depends on the angle that you're moving at. That's what this theta is here, or rather where you are in coordinate space. We don't have to go over the calculation here, but the point is, thank you for the like, Smally Pants. We don't have to go over the calculation here, but the point is you can actually just calculate, once you know what n sub I is, and you can just do these calculations. It's a mess, but there's nothing like clever that you have to do. And so this is the energy density that you end up with. Again, remember, it's still negative. There's nothing that you can do to make this not negative. But what you can do is you can make it smaller negative, right? The condition for the modulus of this expression to be decreased, meaning that you want this thing to be smaller so that the whole thing requires less negative energy. You need that this thing in the middle, you can square it. You want that this to be less than v squared. Which is, it's just, you're expanding this out, taking a dot product, and then you end up with this formula here. And here, psi is the angle between the vectors r and v. So you basically have the direction at which you're moving in the warp drive, and then you have the direction that you make with the center of the black hole. The violation of the weak energy condition is therefore alleviated under the condition where v cosine of psi is less than this. So this is just a condition, what you need if you want to make the weak energy condition less bad. And so what's the point here? The projection of v on the r-axis. So again, remember, v is a vector. It tells you what direction and how fast you're going in your warp drive. So it's the relationship between your direction vector that you're moving through with your warp drive relative to the direction that you make with respect to the black hole. So think like maybe you're right above the black hole, but you're moving right. Then that angle would be 90 degrees. So the projection on the r-axis should be negative and greater by modulus than 1/2 of this particular value. So the idea here is that if you're what's the statement here, that you want the cosine to be, so you basically want your motion to bring you closer towards the center rather than further from the center. That's what this works out to be. Is that true? Let me just make sense of this. Yeah. So as long as you're moving closer to the center, even if it's not directly towards the center, as long as it's closer to the center, then, then it decreases the amount of energy required. From this, we automatically get the weaker condition that the absolute value of v should be greater than this particular quantity here. Fine. And then they're going to use the null energy condition again. Following 28, we can write the spatial components of the stress energy tensor. It's just a whole mess of a calculation where v is just this particular combination, capital V. Don't worry about this. It's just a mess of a calculation. It doesn't really. There's not a whole lot of intuition to be gained from this. We can actually probably skip most of this. Once again, we can assume without loss of generality that the velocity v is oriented along the x-axis. Okay, fine. Therefore, we have this particular component. Yeah, it's not super relevant, not super interesting anyway. It's just a calculation. If the condition 42 is satisfied, the first term with the rho and the third term with... Okay, let's just read the last sentence here. Besides, as long as y over r and z over r are non-negligible, we also have a second term, which is positive definite, and hence also alleviates the violation. Okay, so they're saying that if you're not moving radially in or radially out, then you can actually get a little bit extra help to make your warp drive, because it'll take even a slightly less negative energy, which is handy. So it's just a big calculation. So yeah, actually they're going to tell us here. This result is particularly useful given that the Schwarzschild metric describes not just black holes, but also generic spherically symmetric masses. That's true. While it's not possible to create a black hole in a lab, one could study the behavior of Casimir plates in the vicinity of a spherical or point-like gravitational source. Cool. Likewise, we can generalize the other results of this paper regarding the warp bubbles crossing black hole horizons. For non-negligible, they're just doing the same thing again. For non-negligible ny and nz, the equation for a light ray along the x-axis. So they're just doing this calculation again, but they're doing the harder version where it's fully general. This is the formula that they end up with. Remember, you're dividing through by dt squared. Then you use the quadratic formula to find the zeros. And then the outgoing geodesic corresponding to the plus sign vanishes when n squared is 1. So we have to demand this. So in particular, you get if you want to be able to escape the black hole, but you're not moving directly radially inwards or directly radially outwards, you get another constraint. So again, if you're at the center of the black hole when F equals 1, the equation is still satisfied when you're subluminal, which also remains valid for very small f. So basically, they say that regardless of which direction you're traveling in a black hole, so long as you're going slower than the speed of light, you'll find that you can actually escape. Very weird. Slower than the speed of light with a warp drive, I should say. Subluminal meaning slower than the speed of light. Huh. Okay, let me drink some water. What's a warp drive here? Literally warp drive. You're contracting space in front of you, expanding space behind you, so you can go at whatever speed you want. It's a warp drive. It's a particular configuration of space-time that lets you move at whatever rate you want. All right. They're also going to talk about thermodynamics. Don't know where they're going to go with this, but let's read. One would also be tempted to ask, how does the warp bubble affect the black hole's thermodynamics? Now, I should explain what black hole thermodynamics even is. Black hole thermodynamics is like this weird analogy. Actually, let me just pull up the Wikipedia article. Black hole thermodynamics, because it's like this weird, it's this weird analogy between normal thermodynamics, which relates to energy and work and entropy and all of these things, and gravity. So let's actually go look up the laws of thermodynamics, and I could just show you by analogy. So zeroth law. So the zeroth law is if two systems are both in thermal equilibrium with a third system, then they're in thermal equilibrium with each other. Okay, let's go look at the black hole thermodynamics. So this is basically saying that if two things are the same temperature, and then if A is the same temperature as B and B is the same temperature as C, then A is the same temperature as C, roughly. So the zeroth law isn't quite the same, but it basically says that the zeroth law here is that the horizon has constant gravity. Is if the black hole's not changing, if it's in equilibrium, then the temperature is constant, which is closely related to this idea. This is basically saying if the system is in thermodynamic equilibrium, then its temperature doesn't change. That's another way of rephrasing this. And so here we see that if the black hole is unchanging, if it's in equilibrium, then the surface gravity, which is related to the temperature, is unchanging. Okay, so let's look at what's the first law of thermodynamics. The first law of thermodynamics is roughly energy conservation, but we want the differential version. Where is the differential version? Maybe on this page? We want the differential version. Where is the differential version? Here's the differential version, right. The differential version tells you that it's this one that we want here. A small change in energy is equal to the temperature times a small change in entropy minus the pressures times a small change in volume. So keep that in mind. Here, we have a similar thing. If you have a stationary black hole and an unchanging black hole, and then you perturb it just a little bit, you can talk about how much the energy of the black hole changes based off of the perturbation. So the change in energy is related to change in area. Remember, area, actually don't remember. So area here area is playing the role of entropy. So we have S, that's entropy. We have A is area. Kappa here is surface gravity. And remember, the surface gravity was related to temperature in the zeroth law. The zeroth law in thermodynamics says that the temperature is constant if something is in thermal equilibrium. So surface gravity, kappa, plays the role of temperature. And so here we have temperature times change in entropy because area corresponds to entropy. So here we have surface gravity times the small change in area. And then there's other stuff involving charge and angular momentum. But the point is that the first law of thermodynamics, ignoring this PdV term, just the TdS, so that's temperature times change in entropy is equal to total change in energy. For the black hole, it's the total change in energy is surface gravity times change in area. Very strange, but very neat. Now, what about the second law? Second law of thermodynamics, this one's pretty well known. The second law of thermodynamics says that the entropy of a closed system never decreases. So there's got to be I just want to show the formula. Oh, where is it? Roughly this. Delta S is greater than 0, greater than or equal to 0. It's not quite right, but in a closed system, it's close enough. The point is that there's a similar thing for the second law of black hole thermodynamics, which basically says that the area, remember, area and entropy are kind of back-to-back the same. So in thermodynamics, you have entropy. In black holes, you have the area of the event horizon. And so the second law of black hole thermodynamics says that the area is only ever increasing or stays the same. It never decreases. The exception is Hawking radiation, of course. But this is for classical physics. This is a classical result, this black hole thermodynamics. So keep in mind, like, this is all classical. Hawking radiation involves quantum mechanics, so this doesn't play a role. So the idea is that in classical relativity, the area of a black hole never decreases. No matter, you can't do anything to a black hole to make its area decrease. And then you have your third law of thermodynamics. The third law says that you can never get to absolute zero, meaning that you will never approach temperature 0. The third law of black hole thermodynamics says that the surface gravity can never be 0. But remember, the surface gravity was related to temperature, or rather plays the role of temperature. So the idea is that we talk about black hole thermodynamics because there are these weird relationships between energy and temperature and area that behave a lot like thermodynamics do. So they call it black hole thermodynamics. That's the whole story. Right. So let's talk about black hole thermodynamics. One would also be tempted to ask, how does the warp bubble affect the black hole's thermodynamics? Fine, reasonable question to ask. Normally, the Hawking temperature, that's the Hawking temperature here, that is the inverse of kappa. It's 1 divided by kappa, roughly. Sorry, no, it's proportional to kappa. I lied. I was thinking of the... Yeah, no, I lied. I just lied. I was just wrong. The Hawking temperature associated with horizons is proportional to surface gravity. So there is a way. Thank you for the swan, Luna. There's a way that you can associate, like you can literally translate black hole thermodynamics to regular thermodynamics just by an association. So here you just write that the temperature is the surface gravity divided by 2 pi, and it matches up perfectly, which in turn is expressed the time-like killing vector xi. Try pronouncing that, xi. So you can compute what this surface gravity is by using a time-like killing vector. I don't have to explain what a time-like killing vector is. No, I should explain it. A time-like killing vector is basically, it's a way that you could shift your whole space-time without changing the space-time at all. So imagine you just drag, imagine that you look at your space-time, and then you look at your space-time 1 second in the future along your time-like killing vector, and nothing will change. It looks the exact same. That's what it means to be a killing vector. And it's time-like because you're, say, looking 1 second in the future. However, the time-like killing vector is only defined for stationary spacetimes, which is true. There are no time-like killing vectors for non-stationary spacetimes, otherwise they would be stationary. If you have a time-like killing vector, then by definition, your spacetime is stationary. And in our case, it's manifestly dynamical, meaning not stationary. So you have a moving thing. You have your warp drive. So you end up without having a time-like killing vector. And so there's trouble, because how do you actually talk about the surface gravity and hence the temperature? Because you don't have a time-like killing vector, so you can't compute it this way. Notice that the surface gravity shows up in a formula involving the time-like killing vector. If you don't have a time-like killing vector, there's no way to compute the surface gravity. And in fact, this is something I've worked on, talking about how to generalize the notion of surface gravity. It's tricky though. Anyway, so though there have been attempts to generalize the notion of surface gravity to dynamical metrics, there's still no universal definition. Yeah, it's true. It's also not possible to switch to the warp bubble's rest frame, as was done in these references, because in this frame, the black hole horizon would instead be moving. The only reasonable approximation we can make is that the warp bubble is moving very slowly. Thank you for the fruit friends. 42, much appreciated. Yeah. So the time-like killing vector, it's not quite. It's sort of an eigenvalue equation, sort of. Yeah. So what they're going to do is they're going to approximate that the warp bubble is moving very, very slowly, and then you have a nearly time-like killing, or you have a time-like vector that's nearly killing. And then the metric can be considered stationary up to corrections of order v squared. This approximation also makes sense as an approximation of thermodynamic equilibrium. Cool. They say in principle, we can also consider stationary warp bubbles for which the function f is time independent. In this case, the prefactor v in front of f no longer has the physical interpretation of velocity and may instead be understood as just the measure of the distortion of space. So you could have a warp bubble that doesn't actually change in time, but then it's not super clear what it actually is doing. Right. So if you make that approximation where the warp bubble is moving very, very, very slowly, then you have a time-like killing vector, just ones in the front slot. And then you can just compute what kappa is. Don't worry about this. It's called a Christoffel symbol in a set of coordinates. It's related to the first derivative of the metric. And so in the simplest case, you can just compute this. When the warp bubble is much smaller than the black hole horizon, you get a formula for the surface gravity. It's just the lapse function squared times the divergence of the lapse function or the derivative of the lapse function in the x direction with a minus sign. And then at the event horizon, which is where we're interested in doing black hole thermodynamics, you get this. And so in particular, if v is 0 and f prime is, say, 1, sorry, not f prime. If you would want f prime to be 0. So like at the actual center of your warp bubble, f prime is 0. And if v is, yeah, hold on, what? Because this should be like, what, like 8 pi or something like that? Well, let's keep reading. Here, f prime is computed at the characteristic size of the warp bubble, where f is approximately 0, and we neglect terms of order r to the minus 1g. So they're just, they're just taking the derivative of f, fine. F is 0, no, f is 1, f prime would be approximately 0, but it's approximately 0. Oh, no, actually, they're computing this at the edge of the warp bubble, not at the center of the warp bubble. And so f prime is actually going to be large there. And therefore, you can actually just get that the temperature is this. So if v is 0, then you get a temperature here. It's not clear to me what I should think of what f prime is. I guess f prime could be quite large, because f prime is just the rate at which the warp bubble kind of turns off. This result generalizes quite simply to the case when the warp bubble's velocity has a component tangential to the horizon. So imagine that rather than moving inwards or outwards, you're moving along the horizon. Fine. In this case, we have that nx is this component, is this thing, and ny is this thing. Fine. Since nx equals 1 and ny equals 0 at the horizon, the temperature would still be this. All right, let's think about this for a minute. So we have, so this is the old, yeah, okay, so these are the old formulas for the lapse functions. And then they're just taking, okay, they were just generalizing this to the case where you have something that's not directly, not like this very simple warp bubble that's just moving inwards or outwards. This is the temperature of the black hole, by the way. This is the temperature of the black hole's event horizon, which is just related to the motion in the x direction. Fine, it's roughly the same thing that we have up here. Yeah, this is what happens if you take an Alcubierre drive and you put it next to a black hole. That's what we're talking about here, yeah. Okay, now let us consider the issue of entropy. So here's the temperature, great. Under the assumption that it's still proportional to the area of the horizon, that is an assumption. It usually is for stationary black holes, but it's not so clear here. But it's a reasonable assumption, probably. The change in entropy induced by the warp bubble crossing the horizon would give this. So, I don't follow. Are they going to explain? Okay. Yeah. So, this is really interesting, actually. So, the entropy is proportional to the area. And so, remember, when the warp bubble crosses the event horizon, as long as the warp bubble is moving slowly, which it is in this case because the speed is close to 0, the event horizon disappears, which means that the area of the event horizon goes down. So, the change in entropy is, all right, how are they going to compute this? So they say that it's decreasing by this much where they have a cap. and then they have another amount that is decreasing by a base. So let's take a look at this and try to make sense of it. So here they have that A cap, this is RW minus delta. This is the area of the spherical cap that is part of the warp bubble behind the black hole horizon. So in this picture, it's the area of this piece. It's that area there. And then we have a base, which is the area of the base of the cap that is also part of the black hole horizon, cut out by the warp bubble. Part of the warp bubble. Ah, okay. Okay, I see what they're saying. So that's this area here. Oh, okay. So I don't know how to point. Okay, so A base is the black line connecting where the dotted line intersects with the dotted line again. And then the A cap is the piece of the blue dotted line that's to the left of the black line. Right, okay, it's just some fairly straightforward geometry to compute these areas. That's how they're getting these. Right, this is the area of the base of the cap that is also part of the black hole horizon cut out by the warp bubble, where RW is the radius of the warp bubble and delta is less than capital RW is the distance between the center of the bubble and the black hole horizon. As A cap is greater than A base, so the round part is bigger than the base part, of course that kind of makes sense, and F double prime is very, very big. Why aren't these in polar coordinates? Oh. Well, they kind of are, at least a little bit. F double prime is very, very big. That's the rate at which the warp bubble turns off. The positive term, oh, and they're assuming that the Schwarzschild radius is very, very small. The positive term in 60, so that's, wait, what positive term? There is no positive term. Am I hallucinating? There is no positive term, right? F cap is positive, right? Or F prime is positive. RW is, this is, I mean, these areas are positive. Let's keep reading, maybe they'll explain. Sorry. The positive term in 60 would be greater than the negative second, than the positive first. Okay, for some reason they're asserting that this is positive. I don't know why that would be true. V is small. Maybe, no, I'm sorry. F prime is negative. No, F prime is very negative. Which is weird that they would write this. But F prime should be very negative because it's going from 1 to 0 very quickly. Right, so F prime is very negative. So, okay, that kind of checks out that this term is positive. The first term would be greater than the negative second. So they say that A cap is greater than A base, and F F prime is much greater than 1 over RG. They really should have put opposite values here, because otherwise it's just false. And so yeah, so they say that under these conditions, this positive term is bigger than the negative term, and so the overall change in entropy would be positive, probably exactly as expected, which means that the warp bubble is amenable to black hole thermodynamics. That's good. What it's basically saying is that the event horizon actually does get bigger, or rather, the area gets bigger, which means that the entropy gets bigger. So the second law of thermodynamics for the black hole still checks out for a warp bubble that's intersecting a black hole event horizon. The way to think about this is just, look, and this is really a rough way, but the event horizon becomes the black line up top, and then it traces out the blue line to the left, and then it traces out the rest of the black line. And so, of course, the event horizon is going to get bigger because the blue bubble is bigger than the black line between the blue bubble. So it's kind of intuitive, at least. However, it remains unclear what would happen once the bubble is completely swallowed by a black hole, as it's an object with negative energy density, meaning that at face value, it should decrease the mass of the black hole and therefore the entropy. That's a good point. Matters are further complicated if we consider arbitrary warp bubbles that can be compared to or larger in size than the black hole. So if you have a big warp bubble and a small black hole, then maybe it's confused. Let us consider a simple Gedanken experiment and assume that the warp bubble is much larger than the black hole. In this case, instead of the warp bubble crossing the black hole horizon, we would have the black hole passing through the warp bubble. While the black hole is at the center of the bubble, its gravitational field would still be felt by distant observers, but the horizon would be effectively absent. This means that entropy, at least in the original Hawking sense, can no longer be defined, and it leads to other potential paradoxes. Yeah, so, I mean, once you start having warp bubbles that are big compared to black holes, things are going to get confusing. Assuming that warp drives are not a physical impossibility, that's a big assumption, and can be realized in nature, this result would imply a fundamental gap in our understanding of these objects. One possible solution is to attribute entropy and thermodynamic degrees of freedom to the warp bubble itself, even when it's subluminal and hence possesses no horizon. However, such considerations go far beyond the scope of this paper. Yeah, they do. All right, let's read their conclusion. In this paper, we studied the model of warp drive embedding into the exterior of a black hole following the scheme proposed by Ellis. We discovered that the black hole's gravitational field would affect the stress energy tensor of the warp drive, and that under certain circumstances, namely if the warp drive is moving towards the black hole and its velocity is large enough, it can alleviate the violations of the null energy condition and the weak energy condition, and reduce the amount of negative energy density required to sustain a warp drive. This finding bears some intriguing analogs with the Schwinger effect in quantum field theory that involves the conversion of virtual particles into real ones in an external electric field, and may also be instrumental for creating microscopic warp drives within Casimir cavities, such as the one described in 28. Cool. So, to summarize the summary, when you're traveling towards the center of a black hole with a warp drive, it's easier to make the warp drive. Besides, we pointed out that as long as a warp bubble is subluminal, it can effectively remove the black hole horizon. Namely, both an incoming and an outgoing geodesic can pass through the warp bubble's intersection area with the horizon. Interestingly, if a warp bubble is going out of a black hole at superluminal speed, there is a white hole effect, i.e. only outgoing geodesic remains in the intersection region and the incoming one vanishes. So, roughly speaking, if you're trying to leave a black hole, if you're inside the black hole with a warp bubble, let me rephrase. If you're at the event horizon with your warp bubble, then it kind of gives a passage through, so things can leave the black hole by passing through your warp bubble. That's neat. Finally, we analyze black hole thermodynamics in the presence of a warp drive crossing the horizon and find that, assuming certain approximations, namely that the warp bubble is much smaller than the black hole horizon, and is moving very slowly, and the validity of the entropy area law, the warp bubble would produce an increase in the black hole's entropy. However, there are potential problematic issues in other physical situations, namely when the warp drive is completely absorbed by the black hole, it may decrease its mass and therefore its entropy. Confusing. Likewise, when there is a larger warp bubble passing through a black hole, it would produce a screening effect and de facto eliminate the horizon, making it impossible to define the black hole entropy in the Hawking sense. If warp drives are possible in nature, these issues indicate that we still do not understand them from a thermodynamic point of view. And then there's some declarations, acknowledgements. Cool. And here's a bunch of references. So, one moment. So, overall review. I think actually some of this was already known. I'd have to go find the paper, but let me see. Warp drive around Schwarzschild black hole. Let me see if I can find it. Is it this paper? Because I read a paper that was like this. Yeah. So some of this was actually already known. So if I was annoyed... Oh, wait a minute. Hold on. It's the same authors. Okay. It's the same authors. It checks out. Did they cite themselves? Let's see. Because they should have, if it's... They didn't cite that paper. Why didn't they cite that paper? It came out, like, at the end of last year, and they came to roughly, like... They did the same calculations. This is a little bit suspicious, honestly. Did they just take this paper down, or... Why didn't they ever... Where was this submitted? It's not plagiarism. I mean, it's their own work. But I'm just confused as to why they didn't cite themselves. Well, I mean, the thing is like, yeah, it is weird that they didn't cite themselves, definitely. But why wouldn't they? It's just an additional citation. Why wouldn't they want to do that? That's confusing. But anyway, I mean, overall, I actually think the paper is very interesting. It's different paper. It's submitted to a different journal. The part that's nifty, and the part that's genuinely new. So section 3, the warp drive and black hole field, that's actually not new. Although I think that they did do some extra generalizations. The part that's generally nifty is that apparently for falling towards a black hole, it's easier to make it. Wasn't that what citation 22 is? No, it's a different paper. This is this paper, Casimir wormholes. It's just a different paper. Same author, different paper. Which is interesting. They also did the thermodynamics, which is super, super cool. And I'm glad that they did that. So, overall, if only because the results are not so original, 7.5 out of 10, let's say. Very cool paper, though. Very well written, in my opinion. Not any typos. Only one thing that I would complain about, which is this equation. This equation here, f prime should be negative, so it shouldn't be far, far greater than anything. But that's my only complaint. Right. So for everybody who's watching at home, I guess you're all watching at home. For everybody who's watching on YouTube, thanks for sticking around, and I'll see you next week